Well, thank you for such a generous introduction. Not entirely deserved, I fear. I'm very honored to be part of this program today. It's a really great gathering of economists and psychologists, and I hope I can keep up the high standards that I've seen already today. I'm presenting some work which isn't something I've done that much of. On risk elicitation. It's a particular, that is, risk preference elicitation, individual choice problems. And it's with Duncan James, who's written, he was a co-author on the book that was just mentioned, and a former graduate student, now working in Washington, D.C., and a current graduate student. I have about 90 minutes worth of material here, so something's got to give. I think based on what I've heard here, I'll do the theory relatively quickly, and I'll maybe spend time to explain what the tasks are that we're testing. The design gets a little intricate. I'll skip through that and try to spend a reasonable amount of time on the results and concluding remarks. But I'm going to be guided very much from my impressions of what you're interested in and where I spend the time. So first let me say, in terms of motivation, expected utility maximization, and of course there's many very generalizations of that, prospect theory being one of the better known ones, is important. It's treated as if it's something in its own right, but as I see it, its real importance is because that's that you're going to base decision theory, theoretical finance, many other things are based on this. It's very fundamental. So there's a well-established theory or family of theories, but the empirical basis is remarkably fragile. It's been really 70 years since economists have systematic, not just economists, psychologists first of all, and then later economists have tried to elicit risk preferences and use it. And the point of eliciting them is, again, not because there's some object in their own right, but if you could elicit risk preferences, you could use them to predict behavior in areas that are intrinsically important. So far, however, success in terms of eliciting preferences that have really good predictive power, it's quite limited. And that's really the main subject of my book with Mark Isaac, Shyam Sundar, and a co-author on this paper, Duncan James. The point is, though, this is something you need to know. It's a very important input for a lot of research, but there's no consensus yet on what the appropriate methods are. Becker, de Groot, Marshak procedure and variations on that have been used quite a while. The Binswanger menu was used for a long time, starting in the 50s. Binary lotteries became more prevalent and maybe are coming back again. Multiple price lists, Grossman procedures. Recently, balloon tasks and bomb tasks. They've all had their day, and then something else comes along that people like better. Nothing's really stuck so far. So what's the problem? Is it that there's underlying measurement error and we're just still looking for a task that has a smaller measurement error? Is it because subjects are misunderstanding all or many of these tasks? Many of these tasks involve some kind of strategic behavior or bidding, and maybe it's because people don't know how to strategize well. Some people argue that there's preferences, but the preferences are mutable. They change from one elicitation task to the next. A more radical view is maybe there's nothing really there to elicit. We don't want to take a position on these things necessarily, but we want to provide evidence in this study that will compare major ways of eliciting risk preferences and do that in a within subjects manner so we can get a really direct comparison. And we want to do that across a variety of different elicitation methods, and we'll just look at direct elicitation methods where there's no strategizing or bidding or something. You're just supposed to select the preferred object directly. the kind of questions, high level now, the high level questions we're asking are how consistent are the elicited preferences when we compare different direct methods. Is there any systematic way in which the attributes of the task affect the elicited preferences? In order to address, those are our two main sort of high-level questions. In order to address them properly, there's some preliminary issues that we've got to deal with. I had someone say preliminary wasn't the right word here. It's not like these are tentative or something, but these are issues we've got to deal with first. That I think are of some interest in their own right, but not our main concern. So, do people make dominated choices in this sense that I'll maybe mention later, first order stochastic dominance? Do they exhibit some interesting kind of behavior known as disappointment aversion? And one that kind of came up naturally in the way we did the experiments, do people treat prices and probabilities symmetrically in the context that we'll look at, which they should under weak assumptions. Okay, so now I'm going to go to theory. Now, I must apologize as a psychologist, although at the end you might say, aha, as a psychologist I could have told you so all along. The theory I'm going to present in the next few minutes is just economic theory. Here's the way economists look at the problem. So all these elicitation tasks that I'm going to look at, the direct tasks, there's some underlying unknown state of nature, and the main task, there's just two mutually exclusive states, which we'll call X and Y. And the tasks don't necessarily originally phrase it this way, but we can rephrase all these things, put them in a common theoretical framework to say they're all arrow portfolio choice problems. So looked at that way, we have state probabilities which are known. They're explicit, and I think in a credible way. These are given probabilities, mutually exclusive, and each feasible bundle of arrow securities, so many units of the X, so many units of the Y. That means it's going to pay you X points, which translates to dollars or euros in state X. And this many points in state Y. Some of these might be zero, right? So you're only going to get paid in one state, or linear combinations. Okay, so you'd be surprised how many, or maybe you'd be surprised how many different tasks can be phrased in this way. So the way elicitation works is that you offer some feasible set of alternative bundles, X and Y, and the subject chooses one. And then the gamble will eventually be played out, and they'll get either, if they choose bundle X, Y, they'll either get X units or Y units of money when the uncertainty is resolved. So the art of elicitation, looked at this way, is to, for the experimenter to pick the feasible sets that'll provide the most useful information to best reveal the subject's underlying risk preferences. Okay? So looked at abstractly from the economist perspective, that's what it's all about. From the standpoint of standard decision theory, there's nothing else we have to talk about. How the particular manner in which we present the choice set, as long as it's clear and the subject can understand it, it doesn't matter. It's just what's the feasible set, and what do they choose. That'll tell us something about their preferences. Now, to write down specific hypotheses, I want to put some more structure on it. The most standard structure, we don't need this for much of what we do, but it gives a good place to start, a good point of departure, is the expected utility hypothesis, which says that each person is endowed, has somehow, their preferences are summarized by a personal Bernoulli function, an increasing function such that whenever they're faced with a choice, they find the bundle that's available to them that maximizes the expected utility, that is, given probability that the utility associated with X plus the given probability associated with the utility of Y. That's how people make decisions in a sort of baseline model. There are elaborations on that. I'll mention some later perhaps. Now we have some choice tasks that are continuous in the sense that the feasible set is a whole continuum of possible bundles X and Y that are defined by a budget constraint. This is a very familiar notion to economists. And so any affordable combination is available to you, and you want to pick the best affordable combination. If you write down that optimization problem, you get a... I'm going to zip through this kind of quickly, but surprisingly I've never seen this in a textbook. If any of you have sort of seen it done this way, let me know. It could easily be done in a textbook, but I haven't seen it. The key thing is the marginal rate of substitution at the chosen point, if it's an interior point, is defined by the product of a likelihood, that is a probability ratio, and a price ratio. And it's a product, takes that particular form. And it doesn't even mean, even beyond expected utility theory, anything with sort of coherent preferences, smooth preferences, that'll be true for an interior choice. So at an interior choice, the prices and probabilities enter symmetrically in this particular way. So testable implication of pretty much any kind of economic theory on this is that if you write down this composite variable of the log likelihood and log price ratio, that's a sufficient statistic for the whole thing, just that one composite variable. A risk-neutral person is basically going to pick a corner unless this L is equal to 0. That is, except in this condition, in which case they're indifferent. I think I should zip through this. A standard for empirical work, so-called constant relative risk averse utility function, which takes this form. So it's a single parameter, and a way of summarizing risk aversion, risk preferences, is in terms of this parameter. If we had that particular function, we could actually read it off of a regression. So if you put this dependent variable into your regression and you look at the coefficient on this, when you're trying to explain the chosen point, you take the log ratio at the chosen point. You should be able to read right out of that coefficient what the coefficient what their parameter is, their risk aversion parameter. And we'll run these regressions. I'll do some truncation because, you know, this can blow up, so I don't want that. I'll say more about that later. But the point I want to make right here is that even if people have much different preferences than are assumed in this model, you can still run this regression and get a summary of what their risk aversion summarized in a single number, which would be an exact number if they followed the model, but even if it doesn't, it's a number which somehow summarizes a lot of information about their risk preferences. Okay, the time is contracted here. I'm probably spending more time on theory than I should. There's some preference choices on a budget line which people should never take. Let me just show you the picture. Let's suppose that the probability of this is the cheaper good X. This is the budget line. This is Y is the more expensive good. If the probability of X is at least as high as the probability of Y, then any rational person under very weak notions of rationality would pick somewhere on this line. They'd never pick along here. These are first order stochastically dominated. By spending the same amount of money, you can get a higher payoff in both states, a higher payoff in states of given probability along here. So it's a very strong sense in which choices along here dominate. Any choice along here is strictly dominated by some set of choices along here. I hadn't seen that either, but I think some that's known, but I just didn't have seen it written up. Here's something that I think a lot of you have seen in the audience, and we heard an allusion to diminishing sensitivity before. One of the main domains for diminishing sensitivity is with respect to probability, and there's a literature that goes back quite a ways, at least till as back as far as 1954, and maybe even further. Ward Edwards, a psychologist, started to draw curves like this, and it's been used a lot since. Prospect theory, and others will say, people make choices as if they're not using the true probabilities, but some kind of weight on. There's a number of ways of specifying that in detail, but most of them kind of squish the weights towards the weight associated with the probability 0.5, except maybe the very extreme cases. So this kind of S-shape, this kind of slope being less than 1 is called diminished sensitivity. Over the middle ranges, which are the ranges that are relevant to our experiment. So that's one theoretical reason why there may be an asymmetry between, if that at least comes from the literature, why there may be an asymmetry between prices and probability responsiveness. In particular, this would predict, contrary to direct expected utility or generalizations, so many generalizations thereof, that the response, the absolute value of the coefficient on objective log odds is going to be less than that on price, because they're using weights here that push things towards 1. How many people are interested in disappointment aversion from like goal and so on? I'm going to skip this one. It's kind of interesting, but it's a little intricate. It takes a while. We don't want to rest all our work on one particular parametric measure of risk preferences. So it took us about a year of looking around and finally gave up. There's nothing standard that's going to work for all our tasks. So we made up something that's kind of like a lot of things that are in the literature, but a little bit different, which we call relative risk premium. And it's looking at how much expected payoff do they give up at their actual choice relative to what they might have got, and then normalize that by the amount of variability at the expected payoff, the risk-neutral choice. It looks a little like a coefficient of variation or a Sharpe ratio, if you're familiar with those terms. Anyway, it's a second measure that we'll use. Okay, now maybe I'll slow down a little bit. How much time have I burned already of what I got? 25. Yeah, okay, so I burned 10, I've burned 15. 20. I burned 20, oh, okay. I gotta go a little faster. This is now getting a part that I didn't want to zip through quite as fast. What kind of choice task do we have? So subjects will see a budget line like this, and they'll see a probability given like that, and it basically says if heads, this, if tails, it's a fair coin. We're going to flip a coin, actual physical coin later in this kind of case. And they can pick anywhere they want using the slider, using a mouse and slider, any point they want along this curve, and it'll show any tentative choice, it'll show what their payoffs would be in the two states. And then when they are happy with what they get, they click a confirm button, and that's this task. So that's one task. That's a continuous budget line task, BL. It turns out that Eckel-Grossman procedure, which many of you are familiar with, maybe not everybody, can be represented as a particular subset of the budget line that looks like this. Whoops, I cut off here, but this is generally done with 50-50 probability, so it would be the same figure as before. A budget line of a particular slope and 5 or 6 points equally spaced picked on that. If you display it in this space, that's the Eckel-Grossman task. The bomb and balloon tasks also take this form. They have a particular slope to them, particular probabilities attached. A slightly different thing is, how many are familiar with Holt-Lowry multiple price list? Most of you, maybe not everybody. It's a bunch of lines where you're choosing between two particular, one set of prizes, a high prize and a low prize, and a very high and a prize and a very low prize. And the probabilities on the high prices are varying from one line to the next, but each line you got to decide which you prefer. So if you just look at one line, one row of the whole lorry task, that can be displayed as 2 dots on the screen in there, but then you need a different screen because it has different probabilities for the next line. So 2 dots per screen, but a sequence of screens with different probabilities is a task that we're calling budget.halt lorry. And the way you calculate the slopes of the line is just the natural. I don't have time to go through that, but it's just, you know, it's once you tell an Econ 101 student what needs to be done, they can do it. It's not that hard. Here's a new kind of task that I don't think has been done much before. It's just completely equivalent in terms of opportunities and so on with the budget line, but it's displayed differently. It's basically task. Well, this part's sort of physically oriented, but what they read is text. So the way they start with a jar full of cash, and you can't see it. Maybe you can see it here. There's a slider. These have sliders on it that you can move up and down. And as you move the sliders up and down here, if you move it up, then the cash goes down. If you move it down, the cash goes up. The rates at which they move are prices. So in any particular screen, there's a set price for both of the states. And they make their choices this way, and they see in text what the consequences are. So this is, again, what I called elsewhere, the X and the Y that they choose, and this reminds them of the probabilities. Okay? So that's a visually different, but from the standpoint of consequences and choices, exactly the same as a budget line. Multiple price list, I explained to you, each row looks kind of like this. So this is one row, and they stack rows. Okay, so those are the tasks. Well, there's 5 different tasks that we're going to do, and I just went through them. I'm going to just zip through the lines. A little intricate. It's within subjects design. In order to balance things and to make this all fit with each other, there's some things that are done. We can't do, actually there's 6 different tasks. We can only do 5 at a time. We start with the ordinary whole lorry done in text, you know, with a screen full of, well, I think we cut down to 6 rows instead of 10. And also the very last task we do is the same. Always the middle task is a budget line task with a particular sequence of prices, different slopes of the budget line with 50-50 probabilities. And then what happens on either side of that varies quite a bit in a balanced fashion. Yeah, if I had 90 minutes, I could explain this. We ran this with 140 odd subjects, and we pay each subject for one trial, selected randomly, using physical randomization devices that they get to see before we start. They're in and out of there from instructions to playing all these screens in about 1 hour. Okay, so I did get the results with how much time left?
27 minutes.
Oh, okay, not so bad. First, preliminary results. Let me, with 27 minutes, I'm going to list the preliminary results, tell you what they are, and then I'll take a little vote on which one you want me to see explained a little more, you know, what the basis of this so the conclusion on first preliminary result is that dominated choices, stochastically dominated choices, are fairly rare, at least ones where it's not just slightly dominated, but clearly dominated. That's so stochastic dominance, that's the first preliminary result. The second one is that this disappointment aversion model, it has an extra parameter, so of course you can get a better fit, but in terms of predictive ability, it essentially doesn't contribute anything, using some machine learning tricks to establish that. And the third one is about the symmetry of reacting to prices and probabilities. It's rejected strongly in terms of statistical significance. We can reject this especially in the budget jar data, but overall as well. We can reject this symmetry, but not in the direction I would have guessed for any reasons, or what the established literature says. It's in the opposite direction. There's not diminished sensitivity, but excess sensitivity of probabilities relative to prices, mostly attributable to a subset of tasks. Okay, which of these do you want to hear a little more about? In 3 or 4 minutes more. Number 3. Okay, I see some nods. Oh, one. Well, here's some data, of looking by different tasks for particular individuals. We get a lot of different behavior across individuals. Here's a subject that looks like a slightly noisy, but not too bad original Bernoulli utility maximizer. Here's someone who looks pretty much risk neutral for most tasks and disappointment averse for another. Here's one that's much more random and depends on the tasks. Stochastic dominance, that's the one you wanted to see. Well, here's a table which is how many violations of stochastic dominance are there. And the answer is major violations, very few, especially relative to random choice on the budget line or whatever. The paper, I forgot to mention this. Sometimes I give a talk and there really isn't any paper yet. This paper has been actually out there. It's on a website. My lab is LEAPS, L-E-E-P-S. So if you just go to leaps.ucsc.edu and look for the top paper, I just put it up there this morning. So you can find the paper and everything that you might want to know about stochastic dominance is there, especially in the appendix. Disappointment aversion, yes?
What is disappointment aversion? Is this a kind of regret utility? I think I missed it.
I didn't explain it, and I won't, because it's a little bit intricate. It's kind of interesting. I think we'll talk about this on another occasion. I think you'll like it. Except it doesn't really work. Here's the point. It doesn't really work for our data. But it's a kind of a cute theory. Well, maybe you'll be less averse to that after you hear what it is, but I don't know. Anyway, we find that the predictive ability is negligible, at least the size. When you do a holdout sample, you fit this 2-parameter model and then use it to predict a holdout sample. You do that symmetrically over everything. It's not impressive relative to just a 1-parameter model. Okay, so here's the symmetry that seemed to be what people wanted to hear a little more about. The symmetry hypothesis is if you run a regression like this, these coefficients should be, equal and opposite signs, so you can test the hypothesis that they sum to 0 using the usual kind of F test or other tests, but that's the most straightforward one. So we run regressions like this on different sets of data. In column 1 is we're just looking at nice continuous sets where they can surge along a whole budget line, either using that display or other displays. And you'll see that these aren't that far from equal and opposite, but statistically it's highly significant, at conventional levels. So this is about 1.3 versus 1.1. And if you look at all the data taken together, again, it's statistically significant. Depending on what you mean all together. How you include the whole Laurie multiple price list is not entirely straightforward. So you might think of either this one or this one, depending on your opinion of that data, is the most encompassing. And again, there's a difference of, like 1.4 versus 1.2. All right? So that's not huge, but it's an asymmetry. So I have 2 remarks about that. We strongly can reject the null hypothesis. It's in the wrong direction, in terms of what you might have thought, what I might have thought. But still, it's not 1.4 versus 1.2. That's not like a huge difference. And so for subsequent analysis, we'll use that composite variable L without further apology. Okay, now in main results. I'm glad I have some time for that. Different elicitation tasks give you different answers in terms of what's the distribution of risk preferences in this fixed population. We have 142 subjects, and when we use different methods, in a balanced kind of fashion, we get substantially different distributions. Of course, some are closer than others, but and there's some variation for rather similar tasks. But when you look at tasks that in senses that I'll say more about how they differ, when they're kind of further apart in terms of what the task looks like, we get distributions that are further apart. More importantly, in my opinion, the same is true when you look at where people fare. So the fact that you get a different distribution in one than another, well, you could correct for it if a particular person that looks highly risk averse in one task is also highly risk averse in another. But if they're highly risk averse in one task, that same person looks like risk neutral or in another task, and the risk neutral people in this task look risk averse. That's less comforting. So one way of summarizing that is look at the correlations, the rank correlations, experiment rank correlation across tasks. And again, we get decent correlations if the tasks look really similar, but across dissimilar tasks, the correlations, I'll show you some numbers on that, are rather poor. To the point where you might think that, so let me explain how we do this part of the analysis quickly. So we're taking that dependent variable, which can be written in various ways. Here's another way of writing it. And we're going to use that as the dependent variable for this choice with a coefficient that depends on the task. Okay? So we can recover from that a summary measure of risk aversion for each individual in each task by looking at all their data, running this regression. And we're going to use that, apply that to the budget line, budget jar, and I didn't tell you the difference between budget jar and budget jar N. Can you leave cash in, remember you start with a bunch of cash and then you draw down on it to buy up the other securities. Do you have to use all your cash or not? It turns out that you can get the same set either way, the same set of options, of payoffs. And so in this task, the no cash, you're not allowed to leave any in there. So it sort of feels a little different to the subjects, but it should be the same according to standard theory. Consequentialist theory would say they're the same. One other little technical issue here is that since we have to take reciprocals, when we're looking by regression coefficient, we're getting something on the mean, there's a potential Jensen's inequality problem. So we took a look at, we did a quantile regression and found we got it pretty much the same. So that potential problem's not so bad. Anyway, so we use regression-based estimates for these tasks. Then the other tasks that already have standard methods doing it, we can do it either by the regression-based method or the standard method. I'll report the standard method. The one thing that surprised me on how close things were is that whether we use the regression method or the standard method, we get distributions that are surprisingly close, to me, surprisingly close together. It doesn't seem to matter which we do. So those standard methods I won't explain given lack of time. Here's cumulative distribution functions. When I look at histograms, I can't really tell what's going on, but cumulative distribution functions, I think, really tell things apart nicely. So you'll see that these lines, the support of the distribution, the applied risk coefficient of absolute risk aversion, here goes from a little bit positive to about 0.8 or so, and doesn't really go much beyond that in these tasks. Whereas in these tasks, you got these long tails, and they differ quite a bit. Like if you look at the difference in medians, there's a lot of difference across these tasks. So the distributions look different, and the same is true when you look at the relative, that non-parametric measure, relative risk premium. If you look at that, again, you get quite different distributions. Orderings are similar, not exactly the same in terms of the way these different tasks line up. And if you can run standard tests on are these statistically different distributions, the answer is, oh yeah, with one or two small exceptions. Budget jar, no cash, and budget jar cash for some of these measures don't look different. The others all look different from each other. Okay, now to what I think is the more important part is the correlation coefficients. Say, for example, look at Holt-Lowry. Oh, I couldn't explain the design in detail, but half of the subjects are in what we call a fixed price setting, and half of them are in a fixed probability setting, and the tasks that we can do in the fixed price setting include the Holt-Lowry budget dots, but not Eckel-Grossman budget dots, whereas in fixed probability it's the reverse. So these tasks only appear in one, not the other. The other tasks we can do in all trials. It's just the nature of these tasks. We can't do them all in the same session. Anyway, we get correlation coefficients that are really small here. There's a few cases where they're reasonably impressive, and you might think it's just a matter of a measurement error. But in many of these other tasks, yeah, it doesn't look like measurement error. And if you think that you're recovering some underlying, regularity across these tasks, seeing coefficients that are, 0.3 and below is not very helpful. Yeah, in the interest of time, I won't look at some of these variations on it. They get similar results for relative risk premium and as you do for the parametric measure. Okay, now I at least want to tell you what the last three results are, and you'll tell me how much time, whether I can do one or two of these. 13. Oh, great. I can do at least one of these and maybe two. So here's the last set of main results. First of all, some colleagues who saw an early version of this said, as far as I can tell, it looks like it actually could be noise. And if you look at what's called a random coefficient model, which I think is the state of the art in how noise enters subjects' choices, and you say, well, Holt-Lowry is just really noisy, and really, really noisy, and the other is not so, only somewhat noisy, that might explain what you have. So we did a simulation model to give this notion its best shot, and it doesn't work very well. That took us like 6 months to get that out. It shouldn't have taken that long, but it did. And anyway, we worked hard on that, and I think we at least convinced ourselves that there's no way you can explain things by just task-specific noise. The fourth main result, so I gave you the first two, right? The first two have to do with differences in population distribution and in rank correlation. And then the third one is can't explain the rank correlation issue with a simulation model. The fourth and fifth are a little more positive and maybe more welcomed by psychologists than by economists, much as I'd hate to admit that. So things that shouldn't matter from a decision, so econ decision theory says, it's the consequences that matter, the presentation shouldn't matter, as long as it's clear. It turns out, though, in terms of the location, that is the distribution, the mean of the mean and median of the distributions, population distributions of risk aversion coefficients, how that varies across the task, the elicitation task, we can get a lot of a reasonable amount of explanatory power by looking at attributes, mostly that are irrelevant from the standpoint of standard decision theory. These attributes can explain a lot of that variation in location of the population distributions. And number 5 is similar in terms of correlations.
When you say it can explain, you mean if you control for it in the regression?
Well, I'll show you exactly what I mean. I think I'll skip through the simulation exercise. I mean, it won't take me 6 months to explain it, but it will take me more than 6 minutes to probably explain it properly. But it's based on the idea of what's called random coefficients model, which is, if I'm going to explain it, I won't. I'll come back to it. Actually, if we have time and if you're curious about this, I'll say a little more about it. Anyway, we do a bunch of Monte Carlo trials, and if we set things up in terms of the noise amplitude so we can get reasonable results here, results around 50 percentile, so this is the percentile that the actual correlation is among Monte Carlo trials with this. So if we get things around 0.5, that's saying, yeah, the model gives you results that look a lot like the actual data. So we picked noise levels so we could hit this one pretty well, and then everything else goes like to 0 or 1. Well, not quite everything. This one also looks reasonable. This one's not too bad. But, when you see hundreds here, or zeros, or ones, that means that, the actual data just doesn't look like the simulated data. It's way out in the tails. And if we tune other things to do better somewhere else, then it's going to look even worse somewhere else. So the simulation model doesn't seem to account for it. Okay, now we'll get to Axel's question. So looking at points 4 and 0.5, we want to define a set of attributes. We kind of had some of these in the back of our mind when we set up the experiment, but I got to say that, in all honesty, this particular list is something that wasn't pre-registered or anything. It's after looking at data, we came up with this specific list, although it's qualitatively similar to what we had in mind. So is the display in the risk elicitation task a spatial, sort of geometric, like a budget line kind of thing, or is it more text-oriented, like Holt-Lowry and like the jars? 2 dots, so these checks indicate ones that are considered spatial. The dashes are considered non-spatial. The 2 dot attribute applies to the Holt-Lowry original one, also the budget dot version. 6 dots, anyway, I don't have time to go through all this. Here's some attributes apply to a subset of trials, and not all of them. So we have both fixed probability and fixed. The alternative fixed probability is fixed price. We have both kinds of trials for these, and so on. Anyway, we define these attributes, and many of them, maybe all of them. There's some of them you could argue should have maybe slight effects with uncertain sign in standard decision theory. Like when you make a task discrete, instead of the whole line, you just have a subset. That should have some effect, but it wouldn't be a large systematic effect. So, but I can't say 0. But many of these things should have absolutely a 0 effect on what people do according to standard decision theory. So here's what we do. We run the regression, in this case, of the risk preference measures, both. I think this one is the parametric measure, this one's a non-parametric measure. We regress all those observations on these characteristics. And we see that we get some very significant coefficients. So that's what I mean by explain. We have an R squared. It's not an impressive R squared, but we're able to explain for the gamma about a quarter of the variance and more than half of the variance, actually close to 2/3 the variance for the relative risk premium, using these kind of characteristics. So which coefficients come up big? Whether it's spatial or not, subjects reveal more preferences more towards risk neutrality when they're dealing with a spatial display. And that's a pretty substantial shift if you think about the way gamma is scaled. It's if you put in the 6 dot restriction relative to our baseline, you get an even stronger effect in the other direction towards more risk aversion. And then we get a shift back again towards risk neutrality with the restriction for budget dot whole ORI for that side, for that subset of data. If you think about, the difference between risk neutrality, where it has a coefficient of 0, and square root utility, which is very highly risk averse, that's a difference in this coefficient of 0.5. So these are pretty large shifts. If you count for scale, the shifts in the relative risk premium are similar magnitude. All right, I think I want to leave time for questions, right? So let me get into a summary and discussion. We looked at a bunch of, and pretty much all the direct choice tasks that are popular. We were able to fit them into a common sort of framework and looked at individual task-specific summary measures. What we find is that if we look at each task separately, expected utility theory, or if you prefer a simple prospect theory, does a pretty good approximation if you just look at each task in isolation. You get numbers and they look kind of sensible. In particular, the violations of first-order stochastic dominance are mostly pretty small. Effects which are not captured in these generalizations. They don't seem to help predictive power. On the other hand, subjects seem more responsive to probabilities than they are to prices. Not hugely so, but somewhat. Less would have been no surprise, but more is a bit of a surprise. Anyway, it's not doing bad. But if you look across tasks, and here's the point, we want to know, is there something common on there? If you look cross tasking, you try to estimate people's risk aversion with one task and another one that, also well accepted, what the expected utility hypothesis would suggest, and its generalizations, all its generalizations fare poorly in that you get different cumulative distributions, you get different distributions across populations for both of these measures. And and to my mind, more importantly, the ordering of individual subjects revealed risk aversion is very inconsistent across tasks. Well, it's reasonably consistent if they're very closely related, if they match on most of these attributes, but otherwise very inconsistent. So bottom line is that task attributes that are irrelevant according to economist standard decision theory shouldn't matter according to standard theory, but psychologists wouldn't be surprised, right? That these kind of attributes matter, and they seem to in our data. So, thanks very much.